Hello students, welcome to the first tutorial in the Fluids in Motion series. In this video, we're going to introduce the ideas of fluid flow. We're going to look at how we can classify the flow of a fluid into either a smooth flow or a chaotic flow. And then after that, we're going to move on to look at, an example, and that I hope you guys will be able to work it out after we introduce the concept. And then later on, we're going to look at the continuity equation. And then we're going to look at, we're going to have one question that we're going to do in the next video. Okay, so the question at the end is just to help you guys prepare as you practice for the next video. Now let's get right into it. Now, previously we had been looking at fluids in motion, fluids at rest, sorry. So I hope you guys had time to understand that topic. If you haven't seen my videos to that series, I'll leave a link in the description. Yeah, but previously we looked at fluids at rest. Now we want to look at how fluids behave when they move. So we want to see how we can quantify or basically just determine the certain properties of the fluid as they flow. Now, the first thing that we want to keep in mind is this. See, the flow of fluid can be classified into two types. Now, whether the fluid belongs to one type or to the other, we're going to look at how we can determine that. But basically, the flow will either be laminar or it can be turbulent. Now, what do we mean when we say the flow is laminar? Well, when a flow is laminar, what we expect to have is that the fluid here, the particles in the fluid will follow some well-behaved pattern. The paths they will follow will be well-defined. So what you have is particles in one layer will follow one stream, or they will just slide through in one path line, while particles in the adjacent layer or in the next layer will also have their undefined path. The key thing that you have to take from this is, in a laminar type of flow, particles from one stream do not cross to go to the other. Particles will always stick to their stream. Now, these paths that they take are called streamlines. So the paths that the particles will take as they flow are called streamlines. Okay. Now, basically, this is what we're calling a laminar type of flow, a flow in which particles are following their defined paths. Particles never cross from one streamline to the next. The behavior of particles, the velocity of one particle to the next, it's the same. This is, in other words, a well-behaved type of flow, very predictable and well-ordered. A good example I can give you of this type of flow is what you'd expect to see from a smoke. Let's say smoke that is just coming from a source. What you usually observe is that just near the source, of course not always, you see that the flow of that fluid, the smoke in this case, behaves like a fluid. It's going to be well defined. It kind of looks like you can even actually see the streams as they go up. But the further up they go, you realize that at some point it becomes chaotic. Then you see the smoke particles start to literally move in random directions, really. Now, once this occurs, the particles moving in random direction, then we're saying the flow has become turbulent. How does it look like? See, if you had something that was moving like this, well-defined path, when it becomes chaotic or when the flow becomes turbulent, what you start seeing is that particles can start jumping from one path line to the next. So we see this kind of chaotic behavior, something like eddy currents or eddies or wheels will start forming in the fluid. So in other words, the particles just start moving from one point to the other in no random order, really. When we start observing this, then we can say that the flow has become turbulent. Now, mostly when people talk about what causes turbulence, it kind of sides towards the velocity. you hear people say when the velocity becomes high, when the velocity exceeds what is called a critical velocity, then the flow becomes turbulent. But in general, turbulence is not determined only by the velocity. There are a number of key factors that determine whether a flow of a fluid is going to be turbulent or not. To help determine that, we have what we call the Reynolds number. Now, this, you can take it as capital R, or you can take it as Rn, depending on the book you want to use. But of course, let me use Rn here, the Reynolds number. Now, how do we get this? See, the Reynolds number relates a number of key factors. It relates the density of the material, or the density of the fluid, to the velocity of the fluid, and the diameter of the tube, or literally the tube where the fluid is passing. And then this is divided by the viscosity of the fluid. Now, viscosity is something that we're going to look at in a later video, so you guys can look up to that, can look out for that. Now here, of course, you already know what density is, what velocity is, and what diameter is. So of course, in this topic, we're going to work a lot with velocity, and then at some points we'll have to work with volume. So for simplicity, you guys will have to keep in mind that where you see capital V, this will always stand for volume. And where you see small letter v, this is going to be used for velocity. Generally, this is the format that will be used by many books. But of course, just take note of what you're looking at. It should be very easy for you to follow. Okay, back to the Reynolds number. Now, from here, you guys are able to tell that there are a number of key things that actually determine whether a flow is going to be laminar or turbulent. We have the velocity, the density of the fluid, the diameter of the tube where the fluid is moving, and lastly, the viscosity. Now, how do they really affect the flow? Well, we have a range. If the Reynolds number we get when we perform this calculation, if it is less than 2000, then we expect, or we're going to conclude that the flow is going to be laminar, or it's going to be smooth. But if this value, Rn, is going to be greater than 3000, then we are going to conclude that the flow we're getting here is going to be turbulent. Now you might wonder, what is happening between? See, between 2000 and 3000 here, this is more like a transition period where the flow is changing from being laminar to completely being turbulent. But of course, different books will say different things. So depending on the book that you're using, some books will start from 2300 to be the point where laminar ends. Yeah, but in this case, we're going to use 2000 to 3000 as the range for transition, meaning less than 2000 it is laminar, greater than 3000 it is going to be turbulent. So from here you see that to determine this number, of course, again, you will need the density of the fluid, the velocity of the fluid, the diameter of the tube where the fluid is flowing, and the viscosity of that particular fluid. So it's not only the velocity that will determine whether the flow is going to be turbulent or laminar. We'll also have to look at what the density is. We have to look at what the diameter is, and also what the Reynolds, the coefficient of friction is. Now, to just help you guys process what we've gone through, there's a question that you guys can look at. There's a question that you guys can look at just to help you really look at how you can actually work out this question. But perhaps before I even reach that question, the velocity here that we have, this velocity, sometimes this velocity is going to be called a critical velocity. So if the fluid is the same, let's say we keep the same fluid, meaning the density here becomes the same, and then we are using the same diameter here, and then all that we are changing is the velocity. So that value of velocity that the flow can attain when turbulency becomes certain, that velocity is going to be called the critical velocity. So you can just make V the subject of the formula. This is going to become something like this. And then, of course, you're going to be dividing this by density and the diameter. So of course, this expression is going to give you the critical velocity. So in some cases, you might need to use this formula. Just wanted to put it out there. Okay, now with that, let's look at one example that you guys can try out. I hope you'll be able to pull it out. So you guys can pause the video, try to work out this question, knowing what turbulency is and the formula for calculating the Reynolds number and how to use it. I hope you guys will be able to work it out. Okay, now let's quickly go through the question. I hope you guys had time to try it. Let's quickly work it out together. So ideally from the question, we're being told that the aorta in humans has a diameter of about, so the diameter here is given as 2 centimeters. So we can straight away convert this to meters. This is going to be 0.02 in meters. And then next up, at certain times, the blood speed, at certain times, the blood speed through it is about, so here I've been told what the speed is, again, I'm using small letter v, is 55 centimeters per second. Again, I want to use standard units. I want to convert this 55 centimeters per second to meters per second. So I hope you guys will be able to perform the conversion without struggling. So that's the value that we get. Is the blood flow turbulent? So that's the question that we're being asked here. Is the flow turbulent? Then they go on to give us the density of blood, that is 1050 kgs per meter cubic. And the coefficient of viscosity, this is given to us as 2.7 by 10 to the power negative 3 Newton second per meter squared. Okay, so with this information, we quickly go back to the Reynolds number. We know to say if we're going to determine whether the flow is turbulent or not, we need to calculate the Reynolds number for this fluid. So the Reynolds number here, it's going to be determined by the density. So you have the density, and then we have the velocity and the diameter divided by the coefficient of viscosity. So the density here is given as 1050. The units are all standard, so I can drop them here. The velocity, I converted it, I have 0.55, multiplying the diameter, that's 0.02, divided by the viscosity, which is 2.7 by 10 to the power negative 3. So if you work this one out, you should be able to obtain 4277.8 as your final answer. The units are all going to cancel out. I hope you guys, you can try it out, include the units there and see how they play out. But that's the final answer that you expect to get. Now, once we have this value, now we go back to our check. Remember, if Rn is less than 2000, then the flow is going to be laminar. And if our Reynolds number is greater than 3000, then the flow is going to be turbulent. And in this case, we observe that the value we have got, it's definitely greater than 3000. So our conclusion is that the flow is turbulent. Okay, so I hope you guys were able to come to this conclusion as well. Let me know what you think about the method we used. Do you have a nice approach that you used? How did you find it? Yeah, you can leave a comment in the comment section. Otherwise, before we end this, there's just one last thing that I want you guys to just look at, really. Now, you see, here we just determined the classification of the flow, whether it is turbulent or it is laminar. Now, for the most part of this series, we're going to be looking at how the fluids flow, meaning we'll have to look at the flow rate. Now, what is this? We want to look at how fast or how slow a fluid will flow in a particular tube. Now, the thing is, if you have a tube like this, and then somewhere here, let's say we want to find an amount of the fluid that passes this point. I can even label this point A, or Let me label it 1. I want to determine how fast a mass, let's say a mass m of the fluid passes this point. Now, meaning what I want to get is the mass flow rate. So this is the mass flow rate. Now to get this, of course, since it's how much in terms of mass that passes the point 1 in a given time. So that flow rate, for the mass flow rate, we can use J. So this can be capital J. So what we're going to have is the amount of mass that passes divided by how long it took it to pass through that point. So what we get here is the mass flow rate. Now what you guys have to remember is from this expression, we can easily recall that mass can easily be related to density when we divide it by volume. So I'm using rho to mean density, implying that mass is just equal to density times volume. So from here, this expression becomes the mass flow rate will now be equal to the density times the volume divided by the time. So I've dropped the changes. I'm just saying the value for m is just the mass itself, and the value for t is just a change in time. So next up, I also recall that to calculate volume, if I have a shape like this, and I know the cross-sectional area at the base here, and I know this is, let's say, some length x, and this is the cross-sectional area A, then I know to calculate V, all I have to do is multiply A and X, meaning that where there's V here, I can substitute AX. So where A is the cross-sectional area of the tube, and X is the length through which this fluid has moved, or through which the mass has moved. So this is now over T. But then you guys quickly look at this part. This is X there is the distance, the length. T down here is the time, meaning that this ratio here is just the velocity. In other words, now our expression becomes density cross-sectional area multiplying velocity. So this is the mass flow rate of a fluid. So to write it more clear, so the mass flow rate, what we have is the density cross-sectional area multiplying the volume. The velocity, sorry, I just had to make that mistake, right? So that's the velocity. So we use capital V for volume and small letter v for velocity. Okay. Now the key thing is, just as you so to say, we can write this in terms of velocity and area. This came from the mass flow rate. We also have what we call the volume flow rate. From the mass flow rate, you can easily see how how the volume flow rate comes in. But generally, for the mass flow rate, this is the mass flow rate. For the volume flow rate, we're going to use Q to mean the volume flow rate. So this, of course, you guys should be able to see that when you do everything here, you should end up with the cross-sectional area multiplying the velocity as the volume flow rate. So this was the mass flow rate. And then you're saying the volume flow rate is going to end up as this quantity. So this is the volume flow rate. So you can use the same techniques I used to come up with the mass flow rate in this format. You can use them here. It is just going to come out exactly like this. Or generally what you can do, a shortcut that you can do, just divide the mass flow rate by density on both sides. What you end up with is going to be the volume flow rate. That's one way you can do it as well, if you just want to move from here straight away to that. Okay, now lastly, one thing that I want you guys to look at is, if you have a tube, and then inside you have a fluid, and then you pick your boundaries. Let's say this is 1, and then somewhere in front, you can even say that this changes in terms of size. Let's say somewhere here it becomes bigger. Let's say now what we have is something like this. And then let's pick this point as point 2. Now the key thing is, in a specified time, the mass that passes through this point will be equivalent to the mass that passes through point 2. Even though this side, the tube, is of a smaller cross-sectional area, in the end, the mass that will pass through this point in a given time will be equivalent to the mass that passes through that other side. So in other words, we can equate the rates. In other words, the rate of flow of the fluid here will be equal to the rate of flow of the fluid here. So you can say mass over time here will be equal to mass over time the other side. In other words, in terms of cross-sectional area, remember we had J equal to the density, and then we had area multiplying the velocity. But since we are saying the flow rate at 1 is equal to the flow rate at 2, so it's the density at 1, cross-sectional area at 1, the velocity at 1, equal to the density at 2, cross-sectional area at 2, and the velocity at 2. So of course, if the fluid is not compressible, implying that density 1 is equal to density 2, then this expression can be written as cross-sectional area 1, velocity 1 equal to cross-sectional area 2, and velocity 2. This is what we call the continuity equation. Of course, even this can be taken to be the continuity equation. So this is just a special case for when the density 1 is equal to the density 2. But otherwise, this is what we're calling the continuity equation. Okay, so I hope you guys were able to follow. We're going to end the video here. So we'll see how we can use the continuity equation in later videos. So it's something that we're going to use mixed with other concepts. But otherwise, we'll end this here. I hope you guys were able to follow. If you found this video helpful, you can leave a like. If you haven't subscribed yet, make this video that makes you be a subscriber, or I can say it like that. Otherwise, in the next video, what I want you guys to look out for is going to be another or one interesting concept, the Bernoulli's equation. So we're going to look at the Bernoulli's equation. It's very, very simple. You can stick to an equation. I'll show you two methods that you can do this. The first one, we're just going to memorize the formula and see how to use it. In the second method, we're going to see how the whole equation comes up, and then also look at where it comes from, deriving the whole thing. That's going to be a little bit longer. So we're going to leave it for our next video. Okay, otherwise you guys can look up the Bernoulli's equation, see if you're able to work out this question. Then we'll see you guys in the next video. This was your tutor.